Okay, in this example, I want to talk about how to actually work with some explicit vectors and figure out whether or not they're linearly independent. And so what we're going to do is we're going to start with this example. So let's think about these two vectors, 1, 2, and -2, -4. These are both vectors in R2. I'm thinking of R2 as column vectors now for whatever reason, but that's fine. And so I want to know, are these linearly independent? And maybe you can already see what's going to happen, but let's try and do this from first principles, and I think that's a worthwhile thing. We want to know, are there constants, C1 and C2, not both 0, such that the system C1 times the first vector plus C2 times the second vector equals the 0 vector? So again, are there non-zero constants C1 and C2? Just to be more precise, are there constants C1 and C2 that are not both 0, such that this has a solution? Of course, if C1 and C2 are 0, there's a solution. But we want to know, are there any other solutions? And if there's not any other solutions, then they're linearly independent. If there are non-trivial solutions, in other words, if there are solutions other than 0, 0, then these will be linearly dependent. So we have to figure out which one. And if we move these constants inside and then add up the two vectors and then set everything equal to the right-hand side, we end up with a system of two equations and two unknowns. It's almost like there's one and only one problem that we need to solve all semester. So we end up with C1 minus 2C2 is 0, 2C1 minus 4C2 is 0. And now this is a system. We can use all the methods that we've talked about so far and solve it. And when we do that, well, before I spoil it, let's talk about how we systematically could do that. Of course, you can probably look at this and just automatically tell what's going to happen. But one way that we can do that is to look at this as an augmented matrix. So 1, -2, 2, -4, 0, 0. Or you can even look at this as a matrix equation, which I think is the most useful way. 1, -2, 2, -4 times C1, C2 equals 0, 0. So I'm going to call this AX equals 0. So our A is this matrix here. Our variable X is the matrix C1, C2, and the 0 vector is the 0 vector in R2. And so if I want to solve this equation, AX equals 0, let me write this a little better because I'm just, for whatever reason, bothered by the space between the A and the X. But if I want to solve the system, we know that there's already at least going to be one solution, because we can just by hand figure out that when C1 and C2 are both 0, there's a solution. So we know that there's at least one. The question is there exactly one, or are there infinitely many solutions? Because those are the only other options. And so to do that, there's lots of ways that we can do it. But since we have a square matrix, we can use the determinant. And so remember that if the determinant of A is 0, then AX equals 0 has infinitely many solutions. So this will have infinitely many solutions. Otherwise, if the determinant of A is not 0, then AX equals 0 has a unique solution. In other words, it has only the solution X equals 0. So that's going to be the only value that will solve this. That's if the determinant is non-zero. So knowing whether the determinant of A is 0 or not tells us whether or not these two vectors are going to be linearly independent or not. If the determinant is 0, then we get linear dependence because there's infinitely many solutions. In particular, there's some non-zero solution, or there's some solution where C1 and C2 are not both 0. If the determinant of A is not 0, then we have only the solution where C1 and C2 are 0, and therefore they're going to be linearly independent. So all we have to do now really is check whether the determinant is going to be 0 or not. And of course, this determinant will be 0 because you get -4 minus a -4, so that's 0. And that implies that the vectors 1, 2, and -2, -4 are linearly dependent. And maybe you saw that right away, that one of them is a multiple of the other. But just in case you didn't, and this is a general process now, determinants are going to be useful, at least when you have a square matrix. So notice that if we had 3 vectors in R2, we could no longer use the determinant because we'd have a 2 by 3 matrix, and determinants are only defined for square matrices. Okay, so that's an important thing. The determinant's only really going to be defined, it's only well defined for square matrices. So we need the right number of vectors in various vector spaces. Let's do an example using a different vector space. So now let's consider the vector space P2. Okay, and so we're going to consider the vector space P2, and remember that this is the set of vectors of the form ax squared plus bx plus c, where a, b, and c are real numbers. And this is the set of vector space. This is the vector space, which is the set of polynomials of degree at most 2. So it's possible that a is 0. It's even possible a and b are 0. The 0 vector, this is not something that I focused on before, but it's important. The 0 vector is going to be the polynomial 0x squared plus 0x plus 0. In other words, it's the function f of x equals 0. So if you were to graph the 0 polynomial, what you would end up with is the function that's just constantly 0. It goes through the x-axis, in other words. Okay, so this is f of x equals 0. It's the 0 as a function. Okay, so not just as a number, but it's the 0 function, the function that no matter what you plug in, you always get 0. Now, what we need to do is let's take 3 vectors in P2, and I want to determine whether or not they're linearly independent. So our, let's call them F1, F2, and F3. Our F1 of x, let's say x squared plus 4x plus 3. F2 of x is, say, x squared plus 5. And F3 of x, which is going to say x squared plus 4x. Are these linearly independent or not? And so again, just by first principles, what we're going to do is we're going to try and figure out, are there constants C1, C2, and C3 such that C1 times the first vector, again, when I say vector, remember what I mean is an element of a vector space. I no longer mean the arrows that maybe you've seen in Calc 3, or maybe in physics or something. I don't necessarily just mean those. I mean any element of a vector space. So when I say vector, I mean something a little bit more general now. Anyways, we want to solve C1 times F1 plus C2 times F2, so it's x squared plus 5, plus C3 times F3, so that's x squared plus 4x, is equal to the 0 polynomial. Now what's the 0 vector in the polynomial P2? It's the 0 polynomial, so 0x squared plus 0x plus 0. And to have 2 equations always be equal means that these 2 equations are going to be equal for every x value. So you're allowed to plug in whatever x value you want on either side, and these should always be equal. And that's a trick that you exploit in Calc 2 when you do partial fraction decomposition. Another way to do this, another way to say that they're equal, is to take the coefficients and set them equal to each other. So what I want to do is I want to take the left-hand side, and I want to write this as a single polynomial. And we're going to do that by looking at the x squared terms, then the x terms, and the constant terms. So the quadratic term is going to be, let's see, we're going to have c1 plus c2 plus c3 x squared. The linear term is going to be just what we have for the x's, and that happens to be both of these are 4c1 plus 0c2 plus 4c3. That's the coefficient of the x term. The constant term is 3c1 plus 5c2. That's a 5. And we want this to be equal to the 0 polynomial. So in other words, we want the x squared terms to be equal. We want the linear terms to be equal. And we want the constant terms to be equal. Okay, so that's what we need in order for these to be the same polynomial. And so this is going to be 3 equations and 3 unknowns. So we're going to have c1 plus c2 plus c3 is 0. What else? We're going to have 4c1 plus 4c3 is 0. And then finally, 3c1 plus 5c2 is 0. And so this is the system that we're going to try and solve. And it turns out that when we do this, we can write this as a matrix equation. We again have we have three equations, three unknowns. That means that we can represent this as a matrix AX equals 0, where A is square. So that's the matrix 1, 1, 1, 4, 0, 4, and 3, 5, 0. Notice again that the columns, in this case 1, 4, 3, 1, 0, 5, and 1, 4, 0, correspond somehow to the vectors, right? So we have 1x squared plus 4x plus 3. So that's where the 1, 4, and 3 come from. And then x squared plus 0x plus 5, and so on. Okay, so we want to solve this times this matrix A times C1, C2, C3 is equal to the 0 vector. Well, in this case, it's 0, 0, 0. Again, we're thinking of this as somehow encoding information about the polynomial. We'll make this more precise later, but this somehow encodes information about the polynomial that's 0x squared plus 0x plus 0. Right? So again, those are the coefficients there. Just like the coefficients for x squared plus 4x plus 3 were 1, 4, and 3. Okay. And again, this turns into a system of three equations, three unknowns. I really do mean that there's like one and only one question that we need to solve all semester, and this is it. We want to know, is there a non-trivial solution or not? We could write this as an augmented matrix, go through, try and find a solution, and figure out whether or not we have infinitely many or not. That's too much work. All we need is to look at the determinant. So let's look at the determinant 1, 1, 1, 4, 0, 4, 3, 5, 0. And expand along any row or column if you want. There are some zeros that you can exploit, but whatever. If you want to do it, go for it. I'm just going to expand along the first row. So we're going to get 1 times the determinant of the 2 by 2 submatrix, so that'll be minus 20. Minus 1 times the determinant of the 2 by 2 submatrix, so that'll be minus 12. So it's negative 20 plus 12, and then plus 1 times the determinant of the 2 by 2 submatrix, so that'll be 20 minus 0. And our answer is 12. I don't really care what the answer is except to say that it's not 0. And therefore, those three vectors, f1, f2, and f3, are going to be linearly independent. Okay, so determinants can be very useful in determining linear independence, remembering that it all really comes down to solving the matrix equation AX equals 0 and whether or not we have only the unique solution there.